Let us show the frequencies of absorption in such a diagram. Photons with frequency 2 times B will be absorbed, 4 times B will be absorbed, 6 times B will be absorbed, and so on, according to the results that you see here. Now, relative intensities are proportional to the initial populations. This is relative intensity. And if you take the first transition as 1 unit, for example, 1 centimeter height, this corresponds to 0 to 1 transition, and the photon frequency is 2 times B. The height of the next line is 2.7 times the initial, the first one. So this is, the height here is 2.7 times the height of this one. So if you take this as 1 centimeter, the height here is 2.7 centimeter. This is the line which corresponds to 1 to 2 transition. In other words, molecules initially in J equals 1 are making a transition to J equals 2 level, and the energy difference is 6B minus 2B, 4B. The next absorption is at 6B. Here the transition is 2 to 3. And after that, we have the transition 3 to 4. Then at 10B, it starts decreasing. Such a graph is called line spectrum. Because of the vertical lines in our picture. Microwave instruments, which are used in such experiments, they produce this type of diagram, but completely experimental results. What do we see? We see that the highest intensity is at 8B. Photons whose energies are 8B are absorbed more than any other frequency photons, the highest intensity. This is because the population of J equals 3 level is the highest population. Note that the difference between one frequency and the next one, this difference is 2B. Now, difference between this line and that line is also 2B. And same is true for all successive lines. So this is an important characteristic of the microwave absorption, that absorption lines are equidistant. the difference between one absorption line and the next one is same. It is 2 times B. So experimentally, if you experimentally determine the line spacing, that will give you value of 2 times B experimentally. From the experimental value, you may obtain B value. You just take the difference between successive lines, divided by 2, it will give you a B value for the molecule you are studying. Fine. Now, this is enough for pure rotational motion and pure rotational transitions. Let us start talking about vibrational motion. Now, in a diatomic molecule, there are just 2 atoms. So if we indicate the 2 atoms by such symbols, this has mass 2, this has mass 1. Vibrational motion is this type of motion. You have 2 atoms, all right? These 2 atoms are connected by a bond, and the motion is in this way. The 2 atoms are vibrating in the diatomic molecule. Now, there is an equilibrium distance. Let us call this distance. Equilibrium distance. Now, there is the definition of vibrational motion is as follows. The molecule has a point called center of mass. During the vibration, the motion must be such that during the vibration, the center of mass does not change. It is fixed in space. And if the motion is making sure that the center of mass is fixed, such a motion is called vibrational motion. And it is necessarily this type of motion, because center of mass must stay at the same place. So when this molecule, this atom is moving to the right by some distance, in order to guarantee that center of mass doesn't change its place, this atom must move in the opposite direction. This is by definition of vibration. Center of mass fixed during motion. The small arrows that I have drawn here indicate the stretch. The distance between 2 atoms are getting larger. But of course, this doesn't continue indefinitely. At some point, the motion stops and then it reverses. Then in the reverse motion, the motion is going to continue. It will pass through the equilibrium distance between the two atoms, and in fact, it's going to continue more. So that in that case, we will call it compression. So if this is the equilibrium, this is stretch, and again, this is equilibrium. This is contraction. So the motion is concerted. The two atoms move together because the center of mass must stay at the same place. Part of the time, the molecule is stretching. Part of the time, the molecule is getting compressed. So the distance, the bond length between the two atoms is changing during vibration. So let us call this distance R. In this picture, because I have shown the extension, R is larger than R0, but please remember that there is a reverse motion also in which there is contraction, and in the contraction, this R will be smaller than R0. There is an attractive potential energy. This is potential vibrational potential energy function. We are assuming the expression for V is given to us. A typical shape of the potential energy function is as follows. This is 0 for the distance between the two atoms. It looks like values of the potential energy function are positive values according to this picture. Lowest value is at this R value. This is the equilibrium bond length. It is equal to this R0 here. And you see that at the equilibrium bond length, we have the diatomic molecule AB. And as R gets longer and longer, which means as we stretch the two atoms from each other away more and more, then energy is increasing. But at some value for R, the total energy of the molecule AB becomes constant. This means that we have the two atoms are separated from each other by a long distance. But when the two atoms in a diatomic molecule are at a long distance from each other, how do we describe it chemically? The phase symbol gas means we are talking about a single molecule. Initially, AB. This is the bound molecule, AB. But on the right side, what do you see? The two atoms are separated. So what is this? This is dissociation, isn't it? So, at large distance between the two molecules, the energy is constant, the total energy is constant, because it is equal to the total energy of A plus B. And there are no interactions at large distances between A and B. Therefore, energy stays a constant. However, if the distance is smaller, near the equilibrium bond length, there is an interaction between the two atoms, and it is an attractive interaction. They pull each other. So energy gets lower, and the lowest value for the potential energy corresponds to the equilibrium geometry, equilibrium bond length. This energy difference between the minimum and the this constant dissociated situation, this is called dE. D for dissociation, E for electronic. This curve is, or the potential energy function, is obtained theoretically by solving the electronic motion of the molecule. For example, if we apply this to hydrogen molecule H2, there are 2 electrons in hydrogen molecule. So we calculate theoretically, we solve the Schrödinger equation for the motion of 2 electrons as a function of the distance between the 2 nuclei, and that electronic energy curve as a function of R produces this potential energy function, and it has such a shape. The electronic dissociation energy is not the experimental dissociation energy. Please note that, because there is the lowest vibration energy level here is not at 0, but at a higher level. In other words, in this problem, we have a vibrational 0-point energy, and the experimental dissociation energy all right, I'll show it to you later. It is sufficient to say at this moment that this number, this electron dissociation energy, is larger than the experimental true value for dissociation. In other words, experimental dissociation energy is smaller than this number. We will see why. Now, to proceed further, we take this expression and consider its Taylor series around the equilibrium point. So we can write Taylor expansion about R equals R0. We have first derivative evaluated at R0 times R minus R0 plus 1 over 2 second derivative evaluated at R0 times R minus R0 square plus 1 over 6 times third derivative calculated at R0 times R minus R0 cube. It continues like that. This is the standard Taylor series expression. Here V prime means first derivative of V with respect to R calculated at R equals R0. Double prime means second derivative of V with respect to R. You take the second derivative with respect to R and then evaluate at R equals R0. And so on. Let us examine the terms here. The first term is just a number. It's a constant, and the value of the constant, the value of this constant we take as 0. So this is constant taken as 0. Remember, there is an arbitrariness in the potential energy function. If you replace V by V plus C, it doesn't change the situation. So we have discussed this before. Here, the constant is the first term over there, whose value we take as 0. Now, the first derivative. The first derivative evaluated at R equals R0. But what is R0? It is this. What is the value of the first derivative of such a function at this point? Come on, what is the condition for either maximum or minimum of a function? The first derivative becomes 0, isn't it? Therefore, by choosing R0 in this expansion, value of the first derivative is 0 at this point. The remaining terms are not 0. Let us simplify a little bit. Let us call x to be R minus R0 and k is call this k. What is k? Second derivative of the potential energy function calculated at R equals R0. So we write, now we may consider V as a function of x. 1/2 k times x square. This is 0, this is 0. The first non-zero term is this one. Plus 1 over 6 times x cube, and so on. Now, This expression for the true potential energy function is described by two terms by the following definition. This is called harmonic potential. The remaining part is called anharmonic. Therefore, there are just two terms here. One is harmonic, the other is anharmonic. What is the definition? You look into this series expression. There is just one term up to which depends on square of x. Remember, x is our variable here, vibrational variable. This part is called harmonic potential. The rest, which contains x cubed, x to the 4, and so on, the rest of it is called anharmonic part. Okay, now we will consider the potential energy function in the harmonic approximation. Harmonic approximation. Here, the true potential energy function, V, is taken as V harmonic. This is V harmonic. One half k times x square. In other words, we are just ignoring the anharmonic part in the vibration potential energy function. Why are we doing this? The reason is simplicity. If we ignore the anharmonic part, then solving Schrödinger equation with this expression for potential energy function is relatively simple, and we can obtain analytical expressions, analytical solutions for the problem. Of course, we must not forget what we have done. This is an approximation. Therefore, when we compare our theoretical results with experimental observations, most of the time we are going to find differences between our results and experimental results, and then we are going to attribute the deviations of theoretical results from experimental results to the anharmonic part of the potential energy function. Now, let us show graphically what we have done for the potential energy function. The true potential energy function is this. But the harmonic potential energy that you see here is a parabola, isn't it? The graph of it. So, but its minimum is the same. Notice that at higher values of the potential energy function, differences between the true curve and the parabola gets larger and larger. Okay? But for lower vibration values of the potential energy, the difference between the true curve and the parabola is not so much. Therefore, we expect this harmonic approximation to work well for low-lying vibrational energy levels. And experimental data supports this conclusion. This quantity or constant that we called K here is called force constant. It is also present here. Now, by looking at this expression, what do you conclude about unit for force constant? Remember, potential energy is energy, all right? So let us use SI unit, SI. Then X has a unit. What is the unit for X? X is distance, meter. This is meter square, isn't it? The left side is energy, joule, which means unit of K must be such that when you multiply unit of K with meter square, you must obtain joule. What does it mean? Joule per meter square. Meter square times this unit will produce joule. This is the SI unit for the force constant. But you may also write it as Newton per meter, force unit. These are equivalent. Newton per meter is the same thing as joule per meter square. Fine. Now the Hamiltonian, we are always starting with classical Hamiltonian and then quantizing it. The classical expression for the Hamiltonian is kinetic energy plus potential energy. This is general, right? For the vibration in the harmonic approximation, for V, we take the harmonic, which is 1/2 kx square. And kinetic energy is square of linear momentum divided by 2 times reduced mass. Now, this expression for kinetic energy, I have tried to explain to you. There is an appendix at the end of this chapter. This is lecture notes 5. At the end of it, last page, I'm explaining kinetic energy in the vibrational motion of a diatomic molecule, and it is this expression. And this is the reduced mass, the same reduced mass that we talked about in rotational motion, which is mass 1 times mass 2 divided by mass 1 plus mass 2. Here are the masses. So, vibrational Hamiltonian, classical vibrational Hamiltonian is kinetic energy, which is this expression, p square over 2 mu plus 1/2 k times x square. Classically, during the vibrational motion, This is equal to a constant. Let us show just the parabola, harmonic potential. This corresponds to x equals 0, this point. This is VH, which is 1 over 2 k times x squared. Now, take an energy value, say this value. This is the total energy, which is given by that expression. Kinetic energy P squared plus potential energy. X is changing. X is our variable. When this energy, the sum of these two, is equal to this value. First of all, note that this is a square. This is also a square here. So these are positive numbers here. When the potential energy becomes the same as total energy, numerically, what does it mean about kinetic energy? You're adding two numbers. One is this number, the other is that number. And the sum is the same number E, because it is the total energy. This is the classical view. Now, if x is such that this 1/2 times k times x squared is equal to E, what does it tell you about the contribution of this term? It must be 0. Now, that x is this x. At this x value, the potential energy is equal to the total energy. And for this to be true, the kinetic energy must be 0, which means P must be 0. Now, if you imagine starting with some lower x value than this one, and then imagine increasing it, then this term is smaller than E. That means there is a contribution from kinetic energy. But if kinetic energy is non-zero, what does it mean? It means it is moving, right? So the motion is like, there is a motion to the right, let us say, moving it to the right, but when it comes to this point, this x value, the motion must stop, because kinetic energy must be 0. This is called turning point, the right turning point. Now, after it stops at this point, the motion is reversed. In other words, what I have described is this stretch. The stretch at a given total energy continues up to a limit. That limit is this value for x here. At this point, the motion stops momentarily and then starts going inward. So then contraction will take place. Remember, x equals 0 means equilibrium. Negative x values means contraction. Positive x values means stretch. it will come to this point. When this point is minus xt, the negative signed value of this one. At this value, because it's a square, this energy will be same as total energy, which means the potential kinetic energy must be 0. But if kinetic energy is 0, that means motion has stopped. So, the vibrational motion takes place for a certain energy, total energy, between these two turning points, classically. You see that as energy increases, the turning points also increase, because this is a parabola. Say, at this energy, we have a larger xt. It depends on the energy. Now, this is an oscillation. Such a motion is called either vibration or, equivalently, oscillation. There is a frequency of vibration. Classically, this frequency, vibrational frequency, we will denote it by the frequency symbol nu, and then attach E here. This E is indicating that this is the frequency at the harmonic approximation. The true frequency could be slightly different than this one. So to make the difference, an E is attached, and it is given by 1 over 2 pi times square root of force constant divided by reduced mass. This is classical frequency of vibration. It is important here to note that frequency expression contains k, but k is a given, it is part of our data. For example, if we talk about hydrogen molecule H2, its force constant is given to us. Also, reduced mass. We just calculate mass 1 times mass of hydrogen times mass of hydrogen divided by 2 mass of hydrogen, which gives us 1 over 2 mass of hydrogen. So that data is given. Reduced mass is given. Force constant is also given. And there is no other thing that we need to calculate frequency. Now, we may imagine different energies, low energy or high energy. You see that frequency of vibration has the same value at all energies, whether at this energy or that energy or that energy. The vibrational frequency, how many times these two atoms are making a round trip? That's vibrational frequency, isn't it? Per second. That number doesn't change. So vibrational frequency is the same at all energies. Now let us then, before starting that, please note that classically it is possible for x to be 0 and momentum also to be 0. So the 0 plus 0 will give 0, which means the lowest possible value for E classically is 0. Of course, expression is telling you that all numbers are positive numbers here. A positive number gives positive number. The lowest is 0, but there is no upper limit for the positive energy values. we will see that for the lowest energy level, quantum mechanically, 0 is not permitted, is not allowed. The lowest quantum mechanical energy is higher than 0. Now let us write quantum mechanical Hamiltonian. This P is replaced with a linear momentum operator, which is explicitly minus I times h bar times first derivative with respect to the x variable. So that quantum expression is square of the momentum operator divided by 2 times reduced mass plus 1/2 k times x square. This is our Hamiltonian operator, and the Schrödinger equation is as usual. Please note that this is the Hamiltonian for the vibrational motion. So, Hamiltonian for the vibrational motion, then this psi will be called state function for vibrational motion, and this E is energy of vibrational motion. And all right, our time is up, and let us continue on next Wednesday.